similar.
Did we ever find the uranium source?
Yes.
What?
Okay.
Well, we don't know the ultimate source, but we know where it was before it was when we found it. But we don't know how it got there because it got there from someplace else.
Oh my.
Yeah.
That's related to the trivia.
Oh, fun. Welcome to Walkabout the Galaxy, the catch-all astronomy podcast where the science is universal, the opinions are personal, and the hosts are here to have a good time.
Yeah. Friday night.
We are strange top and down, the astroquarks, also known as Josh Caldwell,
Jim Cooney,
And Audrey Martin.
coming to you from the Walkabout studio at the University of Central Florida. Charm Quark is recovering from our wild and crazy Dragoncon adventure, and we'll be back next week. Was that your first Dragoncon, Audrey?
That was my first con.
Oh, wow.
Well, I went to that half a day at MegaCon.
Okay, yeah, but this was your
This
first,
was my first-
going to a con experience?
Yep.
Jim, have you ever been to
I've never been to any con other than, I've been to
Au-
stamp expositions.
Audrey, I expect that of, but for you, I'm disappointed.
I agree.
Stamp
I know.
Expedition definitely doesn't count.
Exposition.
Exposition.
Not expedition.
They don't count. It's the same thing, but
No,
just
completely.
everybody is 50 years older. But no, I haven't. I'm just too shy or something like. I don't know. I don't
was
know what
so
Oh my
much
gosh,
fun.
they're awesome.
I-
They're very different now than when I was your age, Audrey.
Oh, yeah?
Yeah, they're they're bigger and they're more commercial. But like when I
Yeah,
was...
there were 70,000 people.
Holy
yeah,
cow!
and that's not even like one of the
That's like
super
the-
big ones. Like
yeah.
MegaCon is almost twice that size.
Really?
Yeah.
Oh, wow.
That's so many people.
And but it's still big. It's a rollicking good time, and I get a kick out of it. Although my scooter got stolen.
I heard. That
Yeah.
sucks.
Was
it tied up outside?
It was locked up, seriously locked up. But yeah,
Wow.
Got
So
stolen?
sometime between 11 a.m. and 5 p.m. So in broad daylight. Yeah.
that sounds really difficult.
Aw.
There were so many witnesses.
Yeah.
I guess they were all in on it.
They were all in on it, right? But when I was younger, cons were sort of like more sort of locally community organized. This one, what I like about Dragoncon Atlanta, one of the things I like about it is sort of community organized, fan organized. But we have these small cons in Denver I used to go to, and Shatner would be there, and Nimoy would be there.
Whoa.
My impression was they were all
Patrick
more
Stewart.
like narrowly like a Star Trek convention. Like it would all be just Star Trek stuff.
No,
But now it
but
seems-
once long ago, yes, there would be conventions with 300 people that were for Star Trek back in the 70s or something. But
Yeah.
Anyway, we had a good time, and that was where we recorded episode 331.
Yep.
And we've done a number of live recorded episodes. Fun to have a live audience. How'd you like doing it in front of an
I
audience?
love an audience.
Yeah.
I love it because I'll make a joke, people laugh. If it's because it's funny,
Whereas
or
here,
because
when you
it's
make a joke,
uncomfortable.
Jim and I just look at you.
Yeah, I just get
with
stares.
blank face.
Yeah.
Yeah. So I can understand why you would.
It's so great.
Yeah.
People clapped for me at one time.
Wow,
I think
nice.
someone mentioned that it was my first con, and
Oh,
I
yeah.
got a round of applause.
That's
it was
a very
during a
welcoming
different.
atmosphere.
I know it was
Right.
really really great.
Yeah. Well, Charm will be back next week. Remember to subscribe to us on all platforms, including Facebook, Instagram, YouTube, and Threads, but not Disney Plus, Paramount Plus, or Apple TV Plus.
Those are all real.
Disney Plus.
I have all those. No.
On YouTube, you will be able to see that Audrey, Addie, and I were in costume.
Oh, that's
You
gonna be
were?
on YouTube. Oh yeah. We didn't show you a picture.
Ah.
Oh,
For
now
the
you're gonna have to
recording.
wait.
Yes, so you can check out our nerdiness in extreme graphic detail on the episode 331 on YouTube. You can contact us anytime at wtg@ucf.edu with questions, compliments, and to find out how to get a cool Walkabout t-shirt. Our Stumper today is conversational. You get to have a 1-hour conversation with a scientist, a real scientist. I was contemplating allowing fictional scientists, but I said no, real scientists, but living or dead. Who do you want to have a chat with, Jim Cooney?
Oh, wow. You sprung that on me. I don't know. You got one?
I thought about it. So the first one that comes to mind is Carl Sagan.
Uh-huh.
But I feel like that's too easy.
Uh-huh.
It's
I mean,
I don't like.
it depends what you're looking for in the conversation. Is this a conversation where you want to learn something that you don't know and get some deeper insights, or is it just like, I want to have a good time talking with a like-minded person?
I think it would be about insights. It would have to be about insights. But like, there's so much that we already know about Sagan because he only died. He died fairly recently, and so we know a good amount. And it would be cool to talk to like one of the ancients,
Archimedes,
or like Hypatia or something
Yeah.
like that. Like that would be kind of cool.
Yeah.
And then like I could be like, oh, guess what? The Earth isn't the center of the universe, and then watch their brains explode.
Right. Yeah. Yeah, I was along those lines thinking of Newton or somebody like that, just because that's
I think,
like, you think of like Einstein is probably the person I would think of first,
That'd be your first
but then
go-to,
that's but that's everybody, and like, he's much more recent. And Newton like was that kind of level of genius, but so long ago that things were very different. I don't know. I think it'd be pretty cool.
I'm thinking I think I would have to go Da Vinci.
Da Vinci.
Ooh, that's a good one.
He
Now,
qualifies as a
that's-
scientist.
Yeah.
I call that a stretch.
Really? You don't call Da Vinci a scientist?
I do not.
I do.
used to.
I totally do.
I will have you know that he made observations and conclusions about, for example, blood flow in the human heart that
Yeah,
was
that's what I
only
was thinking.
confirmed like 20 years ago.
What? That's awesome.
Yeah, he like dissected bodies and stuff, and he took notes.
Yeah.
I call that a
doesn't make you a
scientist.
scientist.
It makes you weird, but you're still a scientist.
He collected data and analyzed it and devised theories about what was going on and how things worked.
Okay.
He wasn't only a scientist,
He definitely was not only a scientist, for sure.
but he was definitely a scientist.
Okay, interesting.
Why do you think he was not a scientist?
I don't know. I just maybe I just didn't look deeply enough into it. I used to in some of my intro classes I had this big list written by some author of like the 100 most influential people of all time.
Yes.
And I would have them try and name the scientists from that list.
Yeah.
And
Try to name the scientist.
try
from
to
that.
name. Did I say try and?
Of course you did.
That's what I do.
Mm-hmm.
And I never included. I mean, Da Vinci was on the list of 100, but I never included him as a scientist. I never gave him a point
So your
for that.
students would say Da Vinci, and you would be like, "No, you idiots!"
Yeah, moron. That's not a scientist.
Yeah.
I don't know.
Wow.
I thought he was just a dabbler.
No.
But if he really made,
yes, he was definitely.
if he was
now,
doing the scientific method, then I'm into it.
he was definitely doing the scientific method. It was arguably more in life sciences.
Yeah, that's fine.
How do bodies and organisms work?
Right.
He did very careful studies of like birds in flight, and I think he was the person who discovered that something about how much time is spent on the downstroke versus the upstroke of birds in flight. Pretty remarkable.
All right.
Well, today we'll talk about hollows on Mercury and baryon acoustic oscillations. But first, this episode of Walkabout the Galaxy is brought to you by hot Jupiters.
Yeah.
Nice.
Combine the dramatic
Good-looking
vistas
Jupiters.
of a gas giant planet with the warm temperatures of the inner solar system with a visit to a hot Jupiter. Thank planetary migration for these surprisingly toasty gaseous planets with icy cores, years ranging from just a few days to a few months, and synchronous rotation with their parent stars. For an extended stay, bring your own space station, as moons are not available on most hot Jupiters. For a different kind of planetary vacation, heat things up with a visit to a hot Jupiter. Hot Jupiters, 7 leagues ahead. And I will give you $20 if you guess what
7
that
leagues
is.
ahead.
What?
Oh, is it an Omega watch? Because you could go, didn't
I mean,
James Cameron?
That's a
Not
good.
at all.
I
took
like
him-
the.
took it
I
down?
like that.
Not
guess.
at all, but
I was going to
no.
say something about boat company.
It's a the reason I was willing to risk 20 whole
Oh, I want to guess again.
U.S.
then.
dollars
7 leagues ahead.
is because
You really need
the
that 20
slogan
bucks.
makes no sense for what it was a slogan for.
Oh,
Which-
okay. Energizer Bunny batteries.
That's it. I'm not giving you $20, Abby. Stop saying things. I'm not,
She doesn't get to eat
kombucha.
tonight
I'm
if
not
you
giving
don't.
you any money.
Um,
Thermidor, which
you
makes
said it
made
first.
ovens. I did say it first. And their very strange explanation for why their slogan was once upon a time 7 leagues ahead,
Thermal
just
door
because they
oven?
were an innovator in electrical appliances.
That's a
They
stretch.
were
So I
like,
looked
we're
for-
so far ahead. We're
That's a
like
stretch.
7 whole leagues ahead.
That's right. I looked for slogans for oven makers for hot Jupiters, and that's what I found. Space news. Virgin Galactic had their 4th, I believe, tourist flight or 3rd tourist flight today, and they didn't even tell me about it.
Oh,
Not only did they
really?
not invite me on board, they didn't even tell me about
Yeah.
it.
Are they
You're
avoiding
a little
you?
further down the list.
Yes, since I didn't pay them $20 or any dollars, I don't think I'm on their list at all. But yeah, they're sort of, reaching a cadence now. I think they've done 4 flights in 4 months.
Okay.
And so that's feeling like a cadence. And they've said their next flight will be in October or in September. So
How many people per flight?
they have 2 pilots.
Uh-huh.
And so far, they've been doing like 3 passengers plus an astronaut handler. They've got Beth
Okay.
Moses is the person.
Oh,
She
okay.
may have. I'm sure she has a different title than astronaut handler, but she's the person back in the cabin. She's the flight attendant.
Yeah.
Who's making sure that everybody's
Like no one's
doing what they need to
freaking
do
out,
back there.
pressing all the buttons.
Yeah, not pulling the emergency
Yeah.
escape hatch or
Yeah.
the fire alarm, and setting off the sprinkler system.
They shouldn't have a fire alarm back there, but they do. It's really mean.
Yeah, and a whole sprinkler system too. It's crazy.
Mm-hmm.
So there are 6 seats nominally, or there can be 6 seats
Mm-hmm.
for people behind the 2 pilots,
So-
I believe. But they have only been flying a total of 6 people, 3 of whom on these flights so far have been Virgin Galactic employees.
So does this make fiscal sense? I mean, if they're charging, you said they were charging like something like $400,000 per seat.
Correct.
So they're making
$1.2
million. Does it cost them more or less than $1.2 million to launch one
I
of those
think
things?
the operation for a flight is probably less than that, but the sunk costs
Right.
of the development
Yeah.
of the system.
So it's going to be a while before they
there's
break
a way
even.
to recoup. There's a ways to go to recoup what it costs to like invent
Right.
that system and go through all the tests and everything, because they've been a company doing things for years. And
Yeah.
So-
Yeah, you would think it would take them a very long time, especially at that cadence. They're going to have to pick it up.
Right. Well, 4 flights in the last 4 months does represent a significant uptick in the
Right,
frequency
right.
for both. So Virgin and New Shepard flying the Blue Origin suborbital rocket. Those are the 2 that are sort of like, we're doing regular tourist flights, suborbital tourist flights. Neither one of them has been doing more than like 2 or 3 a year.
Right.
And so the fact that they've, are looking at their 4th with paying tourists in 4 months next month is pretty good.
Is there going to be a utility purpose for that soon?
Well,
Like-
there was a utility purpose prior to the. Depends on what you mean by utility.
I mean, like, okay, so like you can take an airplane
You
from
can
one
take an
place
airplane.
to another.
True.
But when you take these rockets, you take off and land in, like, it's not. It's only for fun. It's a fun thing.
It's also for science. So they
Okay.
fly. We have flown science payloads, and others have flown science payloads on this rocket. So
But
sometimes
that doesn't bring in the big bucks.
Yeah, it does, because they sell it to NASA.
Oh,
They
wow.
sell the service to NASA.
Wow.
Yeah. So NASA has purchased flights from them
Okay. So
to
it's not going to be
supply
like,
rides to NASA-sponsored payloads.
that's pretty fun. Okay.
Yeah. But it's not transportation. And
No
it is never
transportation.
planned to be transportation.
Okay.
Yeah. It's an up and down.
Up and down.
Yeah.
Got it.
And, there are several reasons why it doesn't have the oomph to go anywhere, is one. You could, in principle, do a short hop, but with
That's what I was
everything-
thinking. Like, you just go up and then kind of like go back down, but then
Yeah.
it's just cheaper to take an airplane.
Right.
And
Bear in mind that this one starts by taking a decent length airplane flight to get up to 45,000 feet or so just to get started. But the rocket motor is not going to get you very far down range, and
yeah.
to go farther down range, you have to go faster, which means you've got to brake harder, and that's a big challenge with
interesting.
human spaceflight. Is braking not too violently and safely
Right.
when you re-enter the atmosphere at high speeds.
Ooh.
That's one of the reasons why these things don't go super high, because you're falling back down. You
Right.
essentially hit the atmosphere like a rock hitting the ocean, and the higher up you go, the harder you're hitting it, and the more difficult it is to dissipate that energy. Other space news, the Chandrayaan 3 mission is now in nighttime and is potentially
Yes.
over, I believe.
Yeah, although I was just looking at it, and there were popular questions on Google about the rover waking up again.
Okay, so as a lander and a rover, they're both
Yeah.
solar powered, which is why nighttime matters. The Chinese had a rover which made it through a couple of, or at least more than one lunar day-night cycle, so it's at least conceivably possible. The lunar nights are very cold because you have no atmosphere to retain heat, and they're long. So things get cold, and electrical equipment doesn't like that. So frequently these lunar missions are planned just for one lunar day.
Yeah, I think it looks like, just from my very quick Googling, that that's going to be one of the tests, is to see if both the lander and the rover wake up again.
Oh, that'll be exciting. So
Yeah.
we'll be able to check in on that in a couple of episodes.
Yeah.
Yeah. All right. And I believe you had some exoplanet updates.
Yeah, so exoplanets have not, I don't know when the first one was found, but
1992, I believe.
I read it now. 1992. So that was when the first one was found. Now we're at over 5,500 exoplanets that have been found and confirmed and all of that.
Right.
And that just blows my mind that we're at over 5,000, that we're at over 1,000 even.
Now, you were born after 1992, is that right?
No,
Thereabouts?
91.
Okay,
91.
thereabouts. So those have all been discovered in your life, in all our lifetimes. But I'm old enough to remember when we were just like, of course there are other planets, but we did not actually know of any of them.
Right.
You know,
How does it feel?
I have to just sort of keep reminding myself of very dramatic changes in our understanding of the universe have taken place in my little pipsqueak of a lifetime.
Yeah.
Which is kind of exciting.
It is. And now, that's enough to do, statistics and stuff, and, not quite big data science, but, medium-sized data science.
Yeah. One of the things that I love about the, we were talking about this earlier, is, of course, that 5,500 number is just going to go up and up and up and up.
Yeah.
Right.
Oh, yeah.
Exponentially. In 30 years, it's gone from 0 to 5,500. The next 30 years, as you say, it's probably going to grow by much more than 5,500.
Yep.
Have you seen these maps that they have done of where those planets are?
No.
So there's three-dimensional maps with the solar system our solar system at the center. And it's where are those 5,502 planets? So a lot of what we've discovered are multi-planet systems.
Yeah.
So the number of planetary systems is a somewhat smaller number, but it's still in the thousands. Because of how we've detected many of them, Kepler looked in one direction in the sky, period, right?
Right.
So there's this pencil beam that extends out from the solar system in one direction that's got a whole bunch of planets in it, more than half are off there, and then there's this smattering sort of scattered around, but they're all super close to us in our little neck of the Milky Way. The Milky Way. Which, we're only...
The tiniest tip of the iceberg.
Yeah. We were talking on a couple episodes ago about the number of rogue planets.
Yeah.
And, of course, we've discovered something like 3, I think.
Well, it's harder to
planets.
discover those.
I know, right. Well, and then because we have discovered the astoundingly high number of 3, when it's so difficult to do it, the conclusion was that there are 1 trillion of them.
Yeah.
And
obviously.
The similar kinds of extrapolations have been made about exoplanets from these discoveries, because the ones we've detected are also, because of how we've detected them, definitely only a fraction.
Oh, for sure.
Even of the nearby space.
Yes.
Right.
Yeah, totally. The geometry still has to work out. We still have to be looking in the right direction at the right time.
Right.
There has to be either like a
calibration
calibration pipeline that can detect it, or like human eyes that are looking for it, or like a lot has to go into it.
Right. Yeah.
But yeah, it's gonna go up exponentially with all the space
So there's probably at least
telescopes.
5,600.
I mean, yeah, maybe like
That's what I'm thinking, or maybe even
5,650.
6,000. Maybe.
Maybe.
Go nuts.
We'll find out.
All right.
And then another bit of space news. Comet Nishimura is currently visible with the naked eye from Earth surface.
Seriously?
Currently it is.
Okay.
It will be, its closest approach is September 12th.
Okay.
Which
will be right about when we're publishing this.
Right.
Yeah. So look in the sky.
Hit pause and run outside right now.
If you're in the northern hemisphere and it's just before dawn.
That's when most of our listeners are checking out the podcast.
That would be an interesting thing to know. Like, what time do people listen to the podcast? I think that would be fun. Or not. That might be super boring information.
Let us know when you're listening.
Yeah. So it'll be brightest on September 12th, but it should still be visible after that too. And if you're in an area where there's a lot of light pollution,
we are.
Then you're out of luck. It's too dim for that. But if you're not, then you should be able to see kind of a green glow.
Yeah.
It's gonna have a different color, so that's really exciting. And I can't tell you which direction to look in because I don't know.
Well, you'll have to check you'll have to look online for your astronomical almanac for that. Later on, we're going to have top quark trivia.
Oh boy!
And our two main topics, we've got a story about Mercury and a story about a cosmological story. Is that fair to say?
Sure.
Baryon acoustic oscillations, which I'm very curious about. One last little tidbit of nerd news. This year is the 50th anniversary of what science fiction milestone?
Science fiction milestone?
The Star Trek animated series.
I wasn't going to come up with that. It's like,
and so there are some they're called very short takes or something, a handful of new Star Trek animated things that are appearing on one of these things where you find Star Trek stuff on.
Good.
Not on the TV.
Who watches
nothing
TV
is on TV,
anymore?
right? Exactly.
My grandma.
Okay, let's start with Mercury Hollows.
Okay, since it is now technically spooky season.
Okay.
We're in the Hollows. Ooh. These are really strange features found in the craters on Mercury that these are features that we haven't really seen any on any other planet. There might be some analogs on Earth, but other than that, these are very unique. So they're super bright. They're very bright features, and they typically are found in what's called the low reflectance material on Mercury. So it's low albedo, dark areas. And it kind of just looks like splotches if you're looking at an image of it from pretty far away. It looks like a disease almost, like a scab or something. But it's not.
Or mold, depending on the color. Depending on the color palette that's used in the
exactly. But
images.
it looks almost like a. It's not. They're not regular. They're not regularly shaped. But they're depressions.
Jim is recoiling in horror.
That was on my arm last week. So
right. Okay. It looks like some
now
disease.
we know where they came from.
So they're these kind of shallow holes almost that have very bright material around the rim, and they can stretch how far?
So bright material. What is
how
There's
bright
bright
is
material.
brighter.
Usually, I'm thinking ice, which it's not because it's on the surface.
It's
of Mercury.
not ice.
We
Or
don't know
salt.
what it is.
But you're kind of like on the right track. So right now, it's still a bit of a mystery, which makes them
Ooh, I
even
like it. That's nice.
spookier. It's a bit of a mystery. First of all, where they came from, how long they've been there. They're probably pretty
They're
new.
relatively young.
They're
right?
relatively young. However, some scientists do think that they are a co-occurrence with the cratering event, that they happened pretty soon after a crater was formed.
Right, so they're correlated with craters.
Mm-hmm.
They have steep sides.
Mm-hmm.
They have this bright material on or
Yes.
around the perimeters of them.
Yes.
And composition uncertain.
Composition uncertain, but some UV spectral data is consistent with high amounts of magnesium sulfate or high amounts of potentially like a calcium carbonate type of material. So like volatiles.
Limestone.
And limestone, yeah, sure. But like volatile material. So, which is weird because there shouldn't be that much volatile material on Mercury, but we already know from Messenger that there are a lot of volatiles on Mercury, and that's another really big question about the planet.
I mean, determining composition and age on objects like Mercury and the Moon and other airless bodies is always a little bit challenging. So, the technique, which you're the expert in, Audrey, of IR reflectance spectroscopy to determine composition is, feel free to dispute me if I overstate this, but it's fraught with ambiguity. I think if that's
so
fair.
offended. No, I think that is fair. And also, I mean, because
there's like the spectral features that you get. I'm a UV guy when it comes to spectra, where you're looking at electronic transitions in atoms and molecules in a gaseous state typically, and those are like razor sharp spectral features that are unequivocally, it's this molecule, it's this atom at this ionization state or whatever.
Right.
It's like very, very pinpoint things. The reflectance spectroscopy from solid surfaces is like, well, there's all these different versions of the minerals, and it's like seeing something at this wavelength is consistent with something having to do with magnesium, but also
that's why it's
the depth,
consistent.
The depth of it is maybe dependent on like how big are the grains of dirt that are in there, and it's like, is there iron in there? How much iron? So it's like it's very difficult.
It is very difficult, and that's why whenever space missions have a lot of different instruments on their spacecrafts, because then you can corroborate the different results from different instruments that you're going to see the elemental composition of something, but if you have a whole bunch of hydrogen, great, but what does that mean in terms of the mineralogy or whatever? So then you can pull out your near infrared spectrometer and figure. So having a lot of instruments is really cool. And there is a mission heading to Mercury, Bepi Colombo, and it's going to take much higher resolution images.
Spatial resolution.
Spatial resolution images of the whole surface, but that also includes the hollows. And so one thing that I know some people that work on the hollows are excited about is seeing, are there smaller cratering events that are kind of on the hollows. That overlie them, because
that'll help with the age.
Yes, because anything that is a little bit bigger than the hollow itself is just going to completely it'll disappear it.
This is another aspect that makes the reflectance spectroscopy of solid surfaces difficult to interpret, because typically your pixel that you're getting your spectrum from includes a big enough area that there's lots of different things in there that are contributing to the spectrum that you see. So that improved spatial resolution will help.
So Bepi Colombo has spectrometers also? I mean, it's not just
I don't
imaging,
actually know.
but also
I don't know.
spectroscopy?
I think.
And then in terms of the age, because we were saying that these appear to be relatively young. How do we determine how old things are on a surface like Mercury or the Moon? Well, how battered is it?
Yeah, crater counting.
So it's relative age data.
Right. So, and then you have to sort of try to find a tie point. Is like, when did this particular thing happen? So there are features that you can kind of get some kind of a tie point. Like Mercury famously has some wrinkles that are believed to be due to solidification of the interior that caused some contraction, and then therefore wrinkling of the crust. And then if you see a crater on top of that wrinkle, it happened after the wrinkle. And from knowing how big Mercury is, you can sort of say, well, the wrinkling probably happened 4 billion years ago. And then you sort of build up your whole history that way, but it's difficult. And then, that's all that happened on Mercury. After that, it's just like more impact after impact after impact after impact.
Right.
Yeah, and so that's kind of related to the hollows themselves. Since they do seem to be really like relatively recent features, what is happening all of that time, all of that time? Space weathering. So one of the ideas is that space weathering is causing some type of reaction on the surface that makes the sulfides within the surface kind of expel the material that is found in the exosphere, in Mercury's exosphere. So the article that we read was talking about sodium and how sodium there's like a sodium tail.
Mercury famously has a big sodium tail.
Yeah.
Which is invisible unless you're looking at a spectrum of the space around Mercury. So it's atoms of sodium.
Yeah. And atoms of sodium don't just pop out of the hollows. It has to do with a more complicated process that I don't really fully understand. But space weathering is an idea that is one of the ideas.
Well, so it looks like one of the reasons it looks like they're young is because we see hollows that are less bright, and those are correlated with regions that are older and more battered. So it looks like the bright hollow, that when a hollow forms, it's bright and dramatic, and then over time it darkens and sort of fades into the background. And so this is one of the reasons why it's particularly interesting and exciting, is like, okay, that means something is happening now to make this weird bright deposit on the surface of Mercury, and we think of Mercury as a geologically not happen in place.
Yeah, yeah. That's what I always claim. It's just like a dead rock. Nothing interesting is happening at all. Yeah. But you're telling me maybe something slightly interesting is happening.
That's right.
Something spooky.
So spoken like a true cosmologist. Yeah. Well, speaking of cosmology, before we get to our cosmology story, we've got special Top Quark trivia today. Why don't you...
Oh, yeah, okay. So, I was thinking recently, because we had an incident at UCF where in one of the storage, Josh, being the department chair, knows much about this. We found some strange uranium in in one of our storerooms or something like that, and at first nobody knew where the heck it came from, and the higher ups were mad just because you don't want to find random.
Well, no one wants that, I assume.
I would say, and this is not spin, that the material was identified through an appropriate process, reported to the appropriate offices, and all appropriate action was taken.
Right. Yeah, all you lawyers out there.
It was all good. It was all good. I don't think. So
and
then
nothing dangerous happened.
Nothing dangerous happened. Everybody's okay. But it got me thinking about radiation. And so the trivia today is related to radiation doses that you would get from various things.
Oh.
And I'm going to have a hard time giving the questions now. I'll give you just the first one because it's just a series of questions about. I'll give you pairs of instances, and you're going to tell me in which one of those things would you receive a higher radiation dose.
Oh, cool. Okay.
So, for example, the first one is you make a telephone call with a cell phone versus you make a telephone call with a banana phone.
Okay.
and you want to know which one of those will give you the higher dose of radiation. And we'll talk a little bit about the the units that you use to measure that, which I confuse the heck out of me. There's all kinds of things.
That's one of them.
Yeah, there's rads, and the one that they often use, I think most commonly maybe is sieverts,
right?
Which is some kind of measure of how much. And when we talk about radiation, it's like a whole bunch of sources. Like if you have a Geiger counter, which is the most famous way of detecting whether there's radiation happening, what's detecting is stuff called ionizing radiation, which could be a bunch of different things. But it's something that has enough energy that when it comes into contact with something else, it has enough energy to knock electrons off of atoms or molecules, and that can be a problem, of course. So but ionizing radiation could be, for example, gamma radiation, which is light. High energy light can knock electrons off of atoms, but so can other electrons or positrons or high energy neutrons, and so all of those things can serve as. And a Geiger counter sees all of those things because it's basically just a thing that can be ionized, and then when it gets ionized, it clicks, and you see that. But that's the dangerous stuff. Of course, early in the 20th century, we didn't know what was doing what. That we just but.
So all right, give us our pairs.
So the pairs are a cell phone or a banana phone, using a cell phone or a banana phone.
Okay.
An arm X-ray or a dental X-ray.
Okay.
So these are pairs. You're going to pick from it.
Yeah, I understand.
A dental X-ray or your background daily dose.
Okay.
And then living at 3 Mile Island, within 10 miles of 3 Mile Island
today
for the whole time. No, while the 3 Mile Island incident was happening.
Okay.
You weren't around for that.
I don't know what you're talking about.
You know what I'm talking about. But many of our listeners will remember 3 Mile Island. Either that or a chest CT scan.
Okay.
Well, this
So
is so
I'm pretty
interesting.
sure I'm going to get them all wrong.
This is so
We'll
interesting.
see. I got a 50% chance. If you get them all wrong,
Speaking
it's very bad luck.
Speaking of things that I'm going to get wrong, baryon acoustic oscillations.
Yeah. Yeah.
You're not an expert in baryon acoustic oscillations?
Not yet. I'm about to be.
All right.
In 5 minutes, I will know everything there is to know about
We'll
them.
see. No, they're challenging, but the easy part of it is we found a really big bubble in space.
In the universe.
In the universe.
We need to always set the scales. Not in the solar system, it's not in the galaxy.
Not in the solar system, not in the galaxy. It's a bubble kind of galaxies or of clusters of galaxies. So this is a structure on the very largest scales of structures in the universe. I mean, when you think of structures, like I said, you have galaxies, which are collections of a few 100 billion stars. And we know that galaxies like to clump together in small units, like our local group, which is like the Milky Way and Andromeda and a couple of other hangers-on. And then galaxies also like to sometimes cluster into clusters of galaxies. And then clusters of galaxies will sometimes be strung together into superclusters of galaxies. And superclusters of galaxies will sometimes be kind of arranged there, or they are arranged in this kind of filamentary pattern, wispy filamentary pattern, great big walls of galaxies and great big voids where there aren't any things. Well, it seems that what they've discovered most recently is a truly colossal structure, kind of a bubble that all of these other structures, like these great walls that we find and stuff, are part of. So all the nearby big structures that you may have heard of before, like the I don't know, what are the ones?
So is this bubble? I'm trying to envision all of what we know, all of the structure in the universe. Is this like the biggest structure that
this is
we
the
know
biggest
of?
structure that we know of? Yes.
Oh.
How big
it is it? On the order of 1 billion light years across.
Oh, I can't. That's so bad. I don't. There's no way I can. It doesn't matter.
Might as well have said blah blah blah.
Yeah,
right?
exactly.
Billion. So this is on a slightly different scale than the depressions in Mercury. Which are, how big were those, by the way?
Oh, yeah.
Meters or kilometers?
No, kilometers.
Kilometers.
Right.
So small. They're small.
Small. Definitely a kilometer small compared to 1 billion light years. Of course, a light year is something like 10 trillion kilometers.
Well, let's see. The galaxy is 100,000 light years.
Right.
So
which is already like too big for my brain to understand.
A million of those would be 100 billion. So it's not a million. So, sorry, 100,000 times 1,000 is 100 million. So it's 10,000 times bigger than the galaxy.
Yeah.
Did I do that right?
Sure. No.
This is why I like
10 to the
asteroids,
fifth.
because you can
10
be
to the
like,
fifth
it's the size of
times 10 to the
Texas.
4th. Yeah,
Yeah,
10,000 times.
10,000.
It's 10,000 times bigger than the Milky Way galaxy.
Cool. Wait, what is?
This thing.
Oh, this thing.
This thing.
Got it.
By the way,
Does
the name of this,
thing have a name?
it does have a name. It does have a name. We're probably not going to do the name justice.
I'm going to do
But
the
I
name.
think,
All right, go ahead,
I
do
think
the name
you need
justice.
to try.
Ho'olelana.
Ho'olelana. I like it. I think
that sounds
I think that's right. I think that sounds right to me as well. So this structure, in addition to just being cool because it's the biggest structure that we have ever yet come across.
What is it? What is it, though?
It's basically a big bubble. So that is.
It's empty.
It's
inside.
a big sphere. It's not entirely empty, but it's emptier inside than on its edge. So
Is there stuff on the outside of it?
The outside. I mean, the bubble is a wall of galaxies in some sense.
Basically, yeah, right. So
Alright,
so
so
the surface of this 3-dimensional, it's just like a big sphere, and the surface of it has a higher density of stuff than the interior or.
I mean, haven't we been mapping
Oh.
out through the Sloan Digital Sky Survey and other things the sort of nearby bubbles and voids and walls and sheets of galaxies for some time?
We have.
Okay, so there's something new here about this BAO business.
Right. So the question is, what is this thing, and what would cause structure on these kind of scales? Because the problem you run into is once you get past just clusters of galaxies, even these big walls and everything, they're not actually gravitationally bound structures. So this isn't, the galaxy holds together because of gravity, and clusters of galaxies hold together because of galaxies. What would cause there to be an organization on that scale, on a scale of 1 billion light years? It's not gravity is not holding this thing in place.
Right.
So why is it there in the first place? And the answer is, they think it's a kind of reflection of what was going on in the universe when the universe was just a few 100,000 years old.
Okay. A remnant, maybe, more than a reflection.
Right. Well, in a sense, yeah. So when the universe is young, there is structure, but it's much smaller. Of course, the universe has expanded since then. So little tiny pieces of structure back then are huge things now. And this BAO thing, the baryon acoustic oscillation, is a way that you make structure in the early universe. So that is, when we look at pictures of the cosmic microwave background, for example, which we love to do.
We do love that.
That's a baby picture of the universe from when the universe was 300,000 years old, and there's little blobs all over it.
Right.
And how big those blobs are is determined by the physics of what was happening in that soup of stuff that existed at 300,000 years.
Which did not include any stars.
No stars, no galaxies. It was all just baryons and photons. A baryon just means protons and neutrons, basically. It's the stuff that stuff is made of.
The nuclei of atoms.
Exactly, and it was a soup of
quarks.
Well,
together, neutrons.
Paired together, right.
Together,
the quarks weren't by themselves, but yeah, it was a bunch of protons, there was a bunch of neutrons, of course the electrons are in there as well, and photons, light is in there as well, and it's all just this great big soup. But the size of the blobs at that point, they could only have been so big.
Because the universe was small.
Well, the universe was small, and the factors that produce those blobs, they're called acoustic oscillations because it has something to do with the speed of sound, right? Basically, if you went into the very, very, very early universe and clapped your hands, right? Then this wave of pressure goes outward, right? There's a little wave of pressure. There's this sound wave that goes out. And if you did that at the very beginning, there's only so far that sound wave could have gotten out
because the universe is expanding.
Before the universe expands so much that pressure waves can't travel anymore, right? Once things get too spread out, then pressure waves can't travel anymore, right? And so you clap your hands really early in the universe, pressure waves start moving outward, and then eventually
they get locked in.
They get locked in at the size, at however far they could have gone from the very beginning to 300,000 years, which is when the universe becomes basically, the light separates from it becomes transparent, and that's when things get locked in. So then you take that size, whatever that size of blob was in the early universe, and expand that out to the size in the universe now, about 1 billion light years.
Okay.
So what this is representing is this, like I said, kind of a reflection or a remnant of the size of structure at the very beginning.
Let me ask you: is the fact that this is a billion light years a discovery or a confirmation?
It's a little bit of both. So it's kind of a confirmation. We had confirmed previously that there exists, that structures like this exist, but not by seeing them directly, but by kind of statistically looking at the distribution of galaxies in the universe and noticing that they're correlated when they're about that far apart.
Okay.
So statistically, we've seen strong evidence for these baryon acoustic oscillations before. We've never seen an actual structure, a single instance of a baryon acoustic oscillation frozen in, and this seems to be it. And when you ask the question, is it a discovery or not? Well, so in that sense, it's a confirmation. They should be there, and we see it.
If we had polled cosmologists and said, how big would BAOs have expanded to at the current epoch?
Right, they would say
would have been about a billion light years.
Now, I said it with an asterisk. This is a little bit bigger than we would have said, just slightly, which means that maybe we have a little bit of explaining to do as far as maybe the universe has expanded a little bit more than we had expected it to, and maybe we have a little bit of a mystery.
So the wording of the abstract is something. So I understood your explanation.
Nice.
But the wording of the abstract says that evidence is presented here for the discovery of a remarkably strong individual contribution to the BAO signal.
Right.
But there is no BAO signal based. I mean, like what you were just describing is like, okay, we're just like measuring the structure of the three-dimensional structure of the universe and interpreting that as the result of BAOs in the early universe.
Yep.
And when I see something like the BAO signal, when I see signal, I think of a detector, that's listening at a certain frequency or looking at a certain wavelength and seeing a certain thing. So is that just a terminology mismatch between my brain and...
Yeah, I think so. I mean, the main data that you take in large-scale structure of the universe is like galaxy counts all over the place. And so when we say BAO signal, we mean correlations between galaxies. Yes, that's exactly right.
All right, cool. And then this particular giant thing, Oleilana.
I like that they named it. I think that's just
awesome. A BAO structure implies a value of the Hubble constant. So is that what gets to like a little bit of tension?
Right. And so the value, you're right, exactly. So the value of the Hubble constant that they get from this is a little bit higher than the value of the Hubble constant that we get from other things.
The Hubble constant again refers to how rapidly the universe is expanding.
Right. Which gets back to it being it's a little bit bigger than it should be.
Because that implies the universe expanding a little bit more.
A little bit faster.
And therefore faster than we would have predicted from other measurements.
If you look at that, the error bars on that they're big-ish.
Relatively big, yeah.
Although the error bar doesn't get you, it's still too high to get you into
where you
accord with all the other stuff.
We're still dealing with Hubble tension.
Hubble tension is there. Yeah. It's real.
Well, at the risk of introducing more tension, let's see how poorly we do on our trivia.
Yeah.
All right, my friends, you got this. You got this. I believe in you.
Me too.
Okay.
Now, you talk for 1 minute. You're talking on your cell phone. You're talking on your banana phone. Which one gives you more ionizing radiation?
Banana.
I think a banana.
It's a banana.
Yes.
Yeah. How much?
Potassium.
That's right. A cell phone actually gives you 0.
Oh, really?
Cell phones don't release any
very
ionizing
low power.
radiation.
Yeah.
Right, they're very low power. They send off a lot of electromagnetic signals, but they're all much lower frequency than you need to ionize anything. And so
that's good.
They are safe. They don't cause cancer or anything like that. But bananas give off. So it's about if you eat one banana, you will because of that ingestion get about 0.1 microsieverts worth of radiation. Okay. Nothing to be concerned about. That's
typically I hear about millisieverts is where you're getting into.
So a fatal dose is about 4-ish sieverts.
Okay, so this is 10 million times smaller than that.
Yeah, it's very, very small, and about 100 millisieverts
is cause for concern.
Is cause for concern. That's the lowest amount that has been linked to anything like long-term risk of cancer or something like that. So bananas, eat your bananas, you're just fine. Unless you eat an insane number of bananas.
Millions of
I
bananas.
knew a dog that loved eating bananas.
Millions of bananas, you might be in trouble.
You might be in trouble. Okay. What about an arm x-ray versus a dental x-ray?
I don't know.
break your arm, or you got to go to the dentist? Which one is going to be worse for you?
I guess the arm, because it's got to go like all the way through.
There's more stuff.
Yeah.
I'd have thought that as well, but it's actually not. A dental X-ray is about 5 times worth. An arm
Really?
an arm X-ray only gives you about 1 microsievert, and a dental X-ray about 5 microsieverts. Still not very much. So
Yeah.
I always thought it'd be a little bit more. I thought those were.
I thought so too.
I was like, if I have bad teeth and I'm gonna have to keep going for X-rays, it's a lot of dangerous. But really, the total amount you get,
Right.
unless you went through an insane number of dental X-rays,
Millions,
still not that.
maybe 100,000.
Yeah. So what about the dental X-ray, which we just said is about 5 microsieverts, versus your daily background dose? We all get radiation from cosmic rays and things like that, or just from radioactive elements in the
daily
Earth.
Daily background.
That's about twice as much. About 10 microsieverts you get
from wandering
That's
around.
still so much
Just from
lower than
living
I
on the
thought
Earth.
it was.
Yeah.
It's
Well,
like if you're like, I don't know, is it different if you're in a city versus out in country, or if you're like at a high elevation?
there are some places, like the Colorado Plateau, for example,
So,
is
like,
higher
high
background
elevation.
radiation because of stuff that's under the ground.
It's
and
mostly,
it's the ground.
Yeah.
it's
because
mostly-
there's a lot of mines out there.
it's mostly that. But still, it's low. But you know.
Okay, got it.
All right. Say you lived within 10 kilometers of 3 Mile Island.
This is a
okay.
place that
For
I
the whole
know
time
so
that
much
happened.
about.
Right.
3 Mile Island, there was a
near nuclear meltdown.
there was a
It wasn't as bad as Fukushima.
Okay.
And certainly not
or
as bad as
Chernobyl,
Chernobyl.
right?
Okay.
But it was a thing that it was all in the
70s,
news.
Late 70s.
Late 70s, or a
remember.
chest CT scan. You know, I've had a lot of those because of kidney stones. You know, so they got to do these CT scans to.
3 Mile Island.
Chest.
Yeah, it's the chest CT. So the chest
Really?
it's only 80 microsieverts for the 3 Mile Island thing. So nothing really. Chest CT scan is like 7 millisieverts.
Oh.
Chest CT scan
Uh-oh.
is
Something
non-trivial.
non-trivial.
Non-trivial. You don't want to have too many of those because because like we said, about 100 millisieverts is the lowest 1-year dose linked to cancer.
Wow.
So if you had 10, 15 of those in a year, that's
You're
linked
getting
to
into
cancer.
that
That's a higher
range.
cancer.
Yeah.
Just some other quick numbers to throw your way before we go. Like I said, about 400 millisieverts give you radiation poisoning. 4 sieverts is a fatal-ish dose. Although in this day and age, if you get it seen fast enough, you might survive that. But a few more than that, 6 or 8, you're definitely dead. 13.4 sieverts was the highest dose received by somebody at Chernobyl, the firemen, firefighters who went in to fight that fire. So they were dead, of course. 50 sieverts is what you'd get if you were stood for 10 minutes near the Chernobyl meltdown. And
Yikes.
155 sieverts is what you'd get if you stood at the hypocenter of the Hiroshima explosion. Obviously, you'd die for many other reasons besides radiation.
What about an MRI? Is an MRI like the same
MRI
as
isn't
it's nothing?
Nothing
because
at
it's
all.
just magnets that are.
Oh, it's magnets.
Yeah,
That's right.
that's the M.
Now you know.
While it may have felt like your baryons were oscillating, it was just another episode of Walkabout the Galaxy. Give us 5 stars and we'll give you the cosmos. Be sure to follow us on Facebook and Instagram to get all our updates. Check out Space Barbie Audrey and Space Barbie Addie and Mirror Universe Spock Josh on YouTube.
Awesome.
Get all our updates. Check out our website at walkaboutthegalaxy.com.
Subscribe to our YouTube channel and catch up on old episodes wherever you get your podcasts.
You can ask us questions via the ancient technology of email at wtg@ucf.edu.
Our theme music was composed by Richard Jerusik. Production assistance is provided by Logan Basinger. Thanks to our listeners in South Africa. Stay safe. I'm Josh Caldwell.
I'm Jim Cooney.
And I'm Audrey Martin.
We're the astroquark signing off until the next episode of Walkabout the Galaxy.
Malk.
Excuse me.